Good evening. My name is Steve Erickson. I'm the program chair for the Geological Society of Minnesota. We've been in existence since 1938. We are aimed at people who are interested in geosciences but are not professionals. We get lectures and laboratories every year at the University of Minnesota, usually at the campus, but tonight we are online and glad to have all of you joining us from all over the country, really. Tonight, our speaker is Zsuzsanna Allerton, who was born in Hungary and came to the United States. And before she became in the geology, she worked as a social worker, a scuba diving instructor, and did some photography as both on land and underwater. And as a photography instructor, she was taking some medical school training, and then made the terrible mistake of taking the geology course, which got her hooked on the whole subject there. So she became a doctoral candidate at the University of Minnesota. She'll talk to us tonight about her work and her research there. She just finished up her thesis back in August and was granted her Ph.D. in September. So please welcome Zsuzsanna Allerton.
Thank you so much. Thank you for the nice introduction. And most of all, thank you so much for inviting me today. I'm very happy to share our research with you. And actually, the biggest part of my dissertation, my PhD dissertation, was focused on hematite and there's a typo. I skipped an E. I'm sorry about that. Hematite ore formation in Sudan, in the Lake Vermilion Soudan underground mine state park in northeastern Minnesota. So the presentation will have two sections, geology and mining history. That's a little bit shorter. And then I will dig into some science to discuss previous research and researchers, their findings. That is the backbone of everything that we did later. And this is going to involve some geochronology. So I'm going to go into some basics to make sure that we are all on the same page. And then I will talk about how that's applied in hematite ore research. And then if there is time, then I'll mention our future work and what we are working right now to advance this research. So let's start with introducing Soudan, Minnesota. That's located in northeastern part of Minnesota within the Vermilion Iron Range near Tower and the lake called Lake Vermilion. I decided to use Canon's map, which displays the iron ranges within Minnesota very nicely. And you can see this arrowhead of Minnesota. Hopefully my cursor is coming through. And then here is Vermilion Range, which is currently inactive. This is where Sudan is. And interestingly enough, if you search online for iron ranges in Minnesota, you might get the number 3. But we actually have 4, because if you see Gunflint Range, I mean, this part is part of Minnesota. So most of it is in Canada, Ontario, but this is Minnesota. And it actually used to be part of the Mesabi Range that has 7 active mines, actually might be more at this point. But it got separated when the Midcontinent Rift System developed. You probably know that the North Shore Volcanics and to its west, the Duluth Complex, that's pretty well known in terms of sulfide mineralization that is part of the Midcontinent Rift System, and it was in place about 1.1 billion years ago, and this emplacement separated the Mesabi from the Gunflint. And then we also have the Cuyuna Ranges that is inactive at the moment. So in my book, that's 4 iron ranges at the moment. And the Vermilion Range is known mostly for the Sudan underground mine, and this is the oldest mine in Minnesota, opened in 1882, and it's also the deepest with 2,341 feet. And when you hear that it's one of the richest iron ore mine, it's richest in terms of ore grade, but I will talk about that in a little bit later. So let's look at geologic history and ancient origins. I Well, not even often. I always use the MGS map from Jersa et al. 2011 because this small inset shows how diverse Minnesota is lithologically. All the rock types we have, it's geologically very rich, at least in my mind. And the area that we are interested in is within this rectangle. This is the Vermilion district of Minnesota. And this area is about 2.7 billion years old. And you will see that with a GA later for the billion years. And it's basically Precambrian time. So these are considered to be ancient rocks. They are also part of the Ely granite greenstone belt. So what you're seeing here is a lot of greenstone that's like basaltic rocks, and then you also have some granites like the Vermilion granitic complex, the Giants Range batholith. Then we have the lower Ely formation, the upper Ely formation. Those are basaltic rocks, and we also have some more sedimentary rocks within the Lake Vermilion formation, and also some volcanic rocks as well as volcanics in the Gifford Lake sequence. But what we will concentrate today on is the Soudan iron formation. And where you see the star, that's where the mine is. And the Soudan iron formation is mainly made up of oxide facies banded iron formation. So they're either dominated by a lot of oxides, but there's also some chert dominant banded iron formations. So that has more of silica layers within them. But these are basically those infamous BIFs, to say it differently, with alternating layers of hematite, iron oxide that's gray or silver gray, and then chert and jasper, so white or red silica layers. So you might have seen photos of it. I'll show you a hand sample later. That's what dominates the Sudan iron formation. And this was also deposited in iron-rich ancient oceans before the Great Oxidation event. So I just wanted to show you a little geologic timeline that's not to scale, but to show how these events followed one another. The formation of the greenstone belt is put to this Neoarchean era within the Precambrian at 2.7 billion. Then we have the Great Oxidation event from 2.4 to 2.0 billion years ago. Then we get to an era between 1.8 and 1 billion where we have tectonic stabilization and mountain building events. So what happens to this beautiful Neoarchean terrain is from the southeast, we get these origins docking into it and building up the continent that we know today. And these origins are the Pinokian, the Yavapai, Mazatzal, and this timing also includes the emplacement of the Midcontinent Rift at 1.1. And then what we see today, the topography, is due to the glacial erosion from 2.6 million years ago to recent times, which is very, very recent. And then there's the present day. So it's not to scale, but just to give you an idea how these events have shaped what you're seeing on the map now. So in terms of mountain building events and also some deformation events, a lot happens in this time scale with the lithologies. And what you see here, I just want to point out a few deformation features that's important in terms of ore mineralization. You see this tower Sudan anticline, and this is from compression. This actually generated faults back in about 2.7 billion years ago. And there are also shear zones. And what these shear zones are, they are also basically the result of these dockings and also some regional events that generated weaker zones. And these weak zones actually serve as conduits for fluid flow. That is, again, very important when we're talking about ore formation. And at this star, we have the Sudan mine, and within this banded iron formation, we have land-shaped ore bodies that are thought to be the result of these fluids affecting the banded iron formation using existing iron from the hematite layers and concentrating it into very dense, high-grade hematite ore bodies. So with that said, let's just talk a little bit about mining. This is actually very interesting, the whole journey of how we got to actually mine high-grade hematite ore. Because Native Americans actually knew about the ore before the Europeans ever actually tried to do anything, and he shared this information with Posey in 1863. Then G-Stunts explored the area in the 1860s, but at that time they were actually searching for gold, and instead they discovered iron ore that was already known, but possibly what wasn't known is the extent of it in this area. And then later, based on A. Chester or Albert Chester, geologist, who actually confirmed that there's high quality, high grade hematite ore in the region, their investments were made to mine this ore. So when we talk about high grade ore, there's a little bit of a gray area there, because if you look at literature, some people actually call banded iron formation ore, but that's actually iron formation, or has an economic significance. So that is put to a percentage anywhere between, some literature says 60, higher than 60% weight percent of iron, and most literature uses higher than 65% of iron. But for example, banded iron formation usually have anything between 20 to 40. So that is low grade, and that is not considered ore. So iron formation and ore are different beasts. And that is important to kind of know when it comes to economic significance. So that being said, the mine opened in 82. They did a lot of test runs, and the first ore shipped 2 years later in 1884. Now, a fun fact, and I don't know if this is true, but in the beginning, 5 years ago when I started, I always misspelled Sudan. Of course, I skipped the U, and that's the region in Africa. But apparently, this was a miner's joke, and that's why it was named Sudan, based on the contrasting winters and Africa's summers. So that's just a fun fact. So, as I said, it all started as open pit mining, 1882. First shipment in 84, and that marked the start of Minnesota's iron industry. Very pivotal situation for Minnesota, but it quickly shifted to underground in the 1900s for safety reasons. I'm not sure if you've ever been to Sudan, but those mine pits are still there. They are fenced around. And if you look down, I mean, you already start wondering how they actually even got out of there. And that is the safety issue. It just became too much of a risk. So what they did, they decided to use the caving method. So they caved in different levels, and that suited the strong hematite ore and the weaker greenstone walls. So this strength and weakness, this is based on material. Iron oxide is pretty strong, and banded iron formation are strong too. And these basaltic greenstone rocks can be somewhat stronger, but because of all the deformation, these greenstones are now they are in a state of being schistose. So what happens is from deformation and even from some burial, the temperature and pressure conditions change, and minerals realign themselves. And they realign themselves in a fashion where they generate these sheets, and these sheets create weak zones. So this is called schistosity, and they are very useful when it comes to migrating fluids, but it's a weaker material. It becomes a weak point. So they actually extracted 15.5 million tons of ore about over 80 years, which is a lot. And there are a lot of drifts and covered a big area. And this was done by mainly immigrants. And according to data, it was like about 20 languages spoken. And it's also close to home, since most of the immigrants were actually Eastern European, and I'm also from Eastern Europe, Hungary. And what they did back then is they made sure to put people next to each other who couldn't understand each other so they could work instead of speak. And even with the conditions, even with having their candles, it was better for them to come to work here and send money home than to work in their own countries, which, yeah, it's how it was back then. But of course, everything comes to an end, and all these operations peaked in 1892 with nearly 600,000 tons shipped that year, operated by two different companies, and the ore was used for steel production. Very important for the U.S. And then, of course, challenges rose and the cost rose as well. It was not economic to sustain this, and that led to decline. But why? It led to decline because of taconite processing. And that's very interesting because that's what's done in the Mesabi Iron Range, and it utilizes low-grade banded iron formation and the magnetite from it. They extract the magnetite, they put it in a furnace, they turn it into hematite, and that's your processed taconite that is used for steel production today. And it's way more profitable. So that led to the ultimate closure of the Sudan mine in 1962. And you're probably aware that there were some other mines and they also closed back then at that time. So the Vermilion Range was done for good. Sudan was donated to the state of Minnesota in 1965 for education and preservation, which is very cool. So that's what brings us to today. And today it's a state park and visitor center. On the top photo, you can see me with one of my PhD advisors, George Hudak, and this was a recent visit to continue our research. And on the bottom picture, you can see a lot of happy people, happy campers, riding along the carts and looking at the fascinating geology. That's to me, it was when I did it for the first time, I could not believe, because less than 5% of the rock exposure in northeastern Minnesota is less than 5%. So there's not much you can see, but underground you're like cruising under shear zones, high grade hematite or banded iron formation. It's very interesting, and I highly recommend the tour. You need to wear warm clothes because it's always 51 Fahrenheit underground, which is balmy during the winter now, and it's a relief during the summer. And yes, I forgot to mention the first part. Yes, the Lake Vermilion and Sudan merged those two parks in 2014, and now it covers over 4,000 acres. And there used to be a physics lab that's empty now. And unfortunately, the underground tours were closed for a while because of the 2024 floods. And I believe that they will be open very soon if they're not open yet. So let's go and dig into science. And I would do no justice if I haven't mentioned all the previous researchers before us. And this is a mouthful. This is a lot of information. You don't necessarily need to read it. Pivotal people: Clemens, Von Hise, Gruner, Klinger, Simons, Thompson. If you look at it between 1967 2015, there's a little bit of a gap. And now we're putting some things on the map, 2025, and hopefully ongoing, maybe the rest of my life, who knows, and other people who are interested in doing it. But there have been quite a good amount of research done in the area. And there are also some consensus. So that's what I'd like to point out here. What we think we know and what we think we could polish a little bit in the future. So I highlighted some words and statements that are coming back in most of these researches. First of all, is that we are looking at ore formation that's a replacement style. What that means is that I mentioned it earlier that these ore bodies are enclosed or within the banded iron formation in like a lane shape. So what we think that means is that the banded iron formation was upgraded to high-grade iron ore. So the banded iron formation is replaced by this high-grade ore. And how this happened is with the help of hydrothermal fluids that actually help migrating iron, and they concentrated it into these very dense ore bodies. So they utilized it from the BIF, they concentrated it in the ore, and what they also utilized is structure. Because these hydrothermal fluids are coming from deep-seated areas, and they need a path to get to the banded iron formation. And we believe that structures like shear zone, these weak zones, were used as conduits to get to the BIF and do the magic and turn it into high-grade ore. So this is something that we agree on pretty well so far. There's more things I'm not going to mention, but what I'm going to highlight today is when this happened, the timing of iron ore mineralization. And there we don't have a consensus so far. Even with our research results, I don't think there's a consensus, but we're going to throw something new on the table. If you look at Clements and von Heis, they have a model, and what it says is that when we had these deformation events, like these shear zones that I showed earlier, that's when these fluids were migrating, and that's when the BIF upgraded to high-grade ore. And that happened at about 2.7 billion years ago, which would make the ore bodies Neoarchean in age. So that's clear, and it comes back with other research as well. Then you look at, for example, Klinger. Klinger did a fantastic PhD thesis and a beautiful, beautiful characterization of ore and adjacent units to characterize them. And he said, well, based on their appearance, geochemistry, these ore bodies are later. And the one very significant event in the region is the Midcontinent Rift System development. So the fluids must have come from there. Therefore, the ores formed about 1.1 billion years ago. Now, that would make the ore Mesoproterozoic in age, still Precambrian, but there's like a 1.5 billion years of in between. That what happened there. Which one is true? That's a long time. We can agree on that. Although you can see a lot of other things here, this is what we're gonna concentrate on today. We're gonna concentrate on ages. Now, you also need to know that these observations give us the relative age of the ore bodies. What that means is that this is based on cross-cutting relationships, based on other units, comparison, geochemistry, even petrography, where you can see what might have come first and later. What we're going to try doing today is to pinpoint this with absolute ages and try to date the ore. And for that, we actually need to use a science called geochronology. So I'd like to go into that a little bit to make sure that we are on the same page. And a lot is written here. I'd like to give you the main part of it. So basically, geochronology is a science that determines the age of rocks or the minerals within those rocks or even geologic events. And it's mainly based on the notion of radioactive decay. What we know that unstable parent isotopes uh, decay into stable daughter isotope. And this has a rate called the half-lives, and this relationship, it's a you can see it on the left image. It's cartoon. On the y-axis shows the parent of the percent of parent isotopes, and then you can see the half-lives, the elapsed time of the half-life on the x-axis. And basically, you see an exponential relationship between this percentage and the half-life. So what you need to know is that we have different, so these little images, these actually depict crystals. And these crystals, then you might have heard of zircon or apatite, these are actually chronometers. And there are different chronometers. We have some high temperature ones, and those are responsible for telling us about the crystallization or the formation ages. And then we also have low temperature ones. And the low temperature ones, they are more like telling us about cooling ages. Why would cooling ages matter? Well, when we actually exhume a terrain, it is going from deeper to shallower, then temperatures change. We also have barrier. If we bury something, then the temperature might go up. And if it's again maybe uplifted, then it cools down, and we can actually measure this now. Also, a key thing to know is assumption, and that is what science is full of, assumptions, right? We assume a closed system. So this system is closed and there's no gain or loss of parent or daughter isotopes after formation or closure, and I will talk about that a little bit later, which is coming. So let's first look at uranium lead geochronology. So this is actually based on the decay of uranium, that's the parent, to lead, that's the daughter. And we have different isotopes, different uranium isotopes, like uranium-238 that decays into lead-206, and its half-life is 4.47 billion years. Why this is important? Because this pair we use for older rocks. And if you look one under, uranium-235 decays into lead-207, half-life 704 million years. That's what we use for younger terrains. So it's very interesting to work out what you can use. You can already know that we are going to be using, and this is why I'm showing this diagram, we are going to be using the uranium-238 to 206 because we're going to be looking at very old rocks. So this diagram, the Concordia diagram, is important because you will see one of our results, and I'd like you to be able to read it and what it means. But what we actually going to do instead of using lead-207 and uranium-235, based on having these measurements, you can also plot lead-207 over lead-206. So there's 3 different plots that you can actually generate. But what you're seeing here is that you have a concordia. This concordia actually has the ages. When we get the information of these isotope ratios, then when we plot on the concordia, we actually get a concordant date. And when we get a concordant date, then we're very happy because then that's just very easy to interpret. But we often actually plot off that concordia line, and then we get discordant dates. And what's interesting, if you have a lot of points and they line up, then we also get a regression line. And when we like physically, visibly pull this line onto this diagram, then it actually can intersect the diagram. And so these disturbances are called lead loss in the system, and these lead losses can be from an event that happened. So for example, if there's lead loss in the event, why would that be? It's because the closed system opens up and we are losing some lead, and then it actually happened a lot after a formation event. Then we plot lower onto the lower intercept that can signify some event. I hope that's clear. I'm not sure if I explained that nicely. It sounded better in my head, but let's go to the next slide, and maybe that will clarify it a little bit. So then we also have the uranium, thorium, helium, and now I'm using the word thermochronology instead of geochronology. So they are, that's a subdivision, and thermo is just telling you that we are looking at a time temperature path. And we also often use uranium, thorium, helium for that because helium actually diffuses out of a mineral very easily because it's very tiny and it's easy to heat it up. And what happens is that now our daughter product, instead of lead, it's actually helium. And what happens is it diffuses out of the mineral at higher temperatures, and it actually stays within the system below a closure temperature. So that's very important because if you look at this diagram on the left, you can see that there's a lot of different thermal chronometers. So there's an interchangeable thing like even uranium, lead, zircon, uranium, lead systems can be used as thermochronometers, but these are high temperature systems. So in order to get this closure temperature, we need to heat it beyond that closure temperature. So for example, for uranium, lead, zircon, and this bottom part, is it about 800 Celsius or higher? So we need an extremely hot event to generate lead loss, if that makes sense. And if we do that, we can maybe even reset it. And that event is the one that will plot on this bottom line here. And then we know that's no longer crystallization because the lead loss actually generated this lead loss. The event generated the lead loss in the zircon. But if you come up here and you look at uranium, thorium, helium, and zircon, or even apatite, and you come to look at the x-axis, you see that there's not a big temperature difference that will make that helium diffuse out of the system. So it's important to know that this is very, for uranium, thorium, helium systems are very sensitive to temperature. And also what we get is not the age. We get the time since the mineral passed through this closure temperature during a cooling event. So in this way, we can actually look at the thermal history of a rock. So why this matters is because we wanted to figure out how we can date the mineralization of hematite. And so previous research shows that some attempt have happened before on iron oxide, but basically what they found, other researchers, is some apatite grain within hematite but those accessory minerals are very rare. And I'm going to tell you now that when we searched for them in the Sudan ore samples, we actually couldn't find them. So then in 2021, we came upon a brand new publication, and this dealt with hematite geochronology. So they basically pioneered a dating method in Perth, Australia, where they found uranium and lead in hematite, and they dated it. So they also used another iron oxide, goethite, for uranium, thorium, helium, for getting some thermal events recorded within, but they used uranium, lead on hematite. So based on this article, we actually collaborated with the first two authors, Liam Courtney Davis and Martin Denisick, and we tried to recreate this. And this is the first time, basically, this was done in North America. So that was very, well, with samples from North America. So that was very, very exciting. So I'm going to give you a little taste of what we dated, how it happened, and show you the results on diagrams. And I will talk you through it, and I'll also talk through the importance of our finding and why it's actually very cool to actually start using new material for dating as the geochronology methods advance. So this is a full slide. And basically, before we start dating anything, we need to characterize the material that we want to use. And we also have to have certain hypotheses based on how we want to tackle it and what we want to get out of it. So as I mentioned it, we had this consensus about the fact that banded iron formation was upgraded to hematite ore. So we went by this, we sampled them, and what you're seeing here on the left top image is a hand sample of banded iron formation. Now, you remember from the pictures that there are these beautiful bands. Well, yes, that's true, but when these banded iron formation get, like even within the mine, they get a little bit altered through all those fluids that are in the area, these hydrothermal fluids. So there is some remnants of bands, but it's very rare to see. But please, you just need to take my word on it. This is a banded iron formation. So what was proposed is that this banded iron formation was upgraded into this very dense microcrystalline hematite martite ore in this case. And this dense ore is what was the prospect of mining back in the days. So as we sampled, we realized that there's actually about, well, in terms of end member, there are two end member textures. So based on hand sample and petrographic analysis that you see on the bottom pictures are photomicrographs taken with reflected light, we actually characterize them as banded iron formation was first upgraded to this microcrystalline hematite martite ore that was somewhat diluted and got into this more heterogeneous texture, which is dominated by microplated hematite within this ore. So how that looks is we only gonna concentrate on oxides right now. You can see these oxides, these are actually magnetites, and they're former magnetites. And we know that because of the cubic structure. And what you see here, these creamy areas, they are the remnant of the magnetite geochemistry. But what's white now, that's hematite. So in this case, they are called martite. That is hematite pseudomorph after magnetite, keeping the cubic structure, but losing the characteristics of magnetite geochemistry. Now, when the hydrothermal fluids pass through, they concentrate the iron, and this martite structure somewhat goes away, and it concentrates all the iron. But so we turn it into a much more crystalline, microcrystalline material. We calling microcrystalline hematite martite. And what you're seeing in between here, these are tiny little rock spaces that are basically empty spaces. As this system evolves, what we notice that these are overprinted by a much coarser type of hematite. So it's a different phase of hematite called microplated hematite, or they grow in larger empty spaces, and they're also coeval, so they are in equilibrium or happy with some chlorite and silicates, and they seem to be late in the game, so to speak. So this is what we actually wanted to date and prove with some geochronology. Now, I can already tell you off the bat that we weren't able to date the banded iron formation, and all the ages that we know is based on cross-cutting relationship of units that can be dated. So in order to date in the uranium lead system, we need uranium. And there's no uranium in here, so we couldn't generate any dates. But we did succeed with microcrystalline hematite martite ore and microplated hematite ore. So what we actually dated here, and that's going to go through with both that's going to be the same for uranium lead and uranium thorium helium, is that we dated this microcrystalline hematite that's white on this middle bottom picture. And then we also dated these coarser microplated hematite to see if we can see their perogenesis or the order of formation in the system and give it an absolute age. And now, here are the results. You've seen this before. The X and the Y axis are slightly different than with the other ones. So we have uranium 238 over lat 206 on the x-axis for both diagrams, and we have that calculation of lat 207 over 206 on the y-axis. On the left one, the blue dots were placed on microcrystalline hematite, martite, or oxides. So that's what we did. And for the microplated hematite ore, it was all microplated hematite itself. So if there's nothing else you take away from this talk today other than the ages, that will be fantastic today. Because if you see, we are neither at the 2.7 billion years mark or 2,700 million years mark, and nor at the 1.1. We kind of shot in the middle a little bit. And this is a Paleoproterozoic age. Now, if you look at the numbers, you would say, oh, look, the microcrystalline hematite martite ore is indeed a little bit older compared to the microplated hematite ore. What you also notice is that the error is pretty high, and that's usual with a new system and a very old system. And it's also not, there's a more precise system versus the laser ablation that we use, but that is, what we have right now is very good. However, when you look at it, the error actually overlaps. So it's very difficult to say that one is definitively older than the other. And I'd also like to point out something else. Remember the Concordia line I talked about. So here's the Concordia line with the ages. Here is the other one. And so what happens if we plot left of the Concordia line, the more leftly we plot, the less uranium we have in the system. And the less uranium we have in the system, and we try to connect these data points, the higher uncertainty we get. So if you look at these numbers on the left one compared to the right one, yeah, we have a lot lower amount. What I didn't mention earlier is that some of these systems has some radiogenic lead to begin with, and that's lead 204. And the microcrystalline hematite martite ore actually began with a lot higher numbers, which already gives us a little bit more uncertainty. And then we had less of it with the microplated hematite ore. And look, we also hit the Concordia line here. But what we're looking at is actually the regression line that goes down all the way and crosses the lower intercept. So for one, it's 1740.4 plus minus 72, and for the other one, 1640.8 plus minus 47.2. Based on this, there might be a relationship, and the microcrystalline might be older than the microplaty. But in this case, what we can say that the ore formed between 1.8 and 1.6 billion years, which is very different, right in the middle between the Neoarchean and the Mesoproterozoic ages. So let's see what happened with the uranium, thorium, helium results. That was a fun one. So this is again a different technique, what you're seeing here. Instead of doing these laser ablation spots and doing, oh, sorry, I forgot to mention it. So in the first one, we did 88 spots. And in the second one, we had 76. So those are spots that are placed in situ onto these, in place onto these hematites. What we do with uranium, thorium, helium, we actually pull shards out. So when we talk about zircon and apatite, those are grains, those are perfect grains. Here we have a very dense system, and we actually breaking shards off. And then we measure these shards. And these shards, I mean, we degas them, we degas all the helium, then we also measure the uranium and thorium separately with wet chemistry, and then we do the magic, and these are the results. Well, I mean, we got a very dispersed data set starting at about 500 million years, and we also going up to about 1600, which is very, very interesting. And we couldn't resolve everything about it, but we did notice a cluster, and that was very important here. There's a cluster right here in the middle. And with kernel density estimation, the age population is about 1100 or 1.1 billion years. So that was very reassuring because it showed up in both samples. And there is still a lot to talk about. Thankfully, we haven't resolved all this. So let's see our interpretation. So we superimposed all this information onto this diagram. And what this diagram shows on the y-axis is all the ages and associated events. So we know when the Pinocchian orogeny happened, these are those mountain building events, Yavapai, Mazatsa, even put the Midcontinent Rift System here, then the followed up Granville orogeny, and then we place the uranium lead dates right in these stars with higher error bars. And then on the x-axis, you see the 8 different shards of each sample. So that's 16 in total. And you can see them dispersed. And this is just to give you a visual of all the information what we have. And so here it comes. So between 1.8 and 1.6 billion years ago, we had these southeast directional hydrothermal effects if they are from these orogenies. And what happened is this is what induced the hydrothermal fluid migration. It reactivated existing shear zones that are Archean or Neoarchean in age. It reactivated them that served as conduits for fluid migration that had iron in it, condensed it, and utilized it from BIF and deposited lens shape iron ore bodies that go deep in the system. We don't even know how deep. So this event is coeval with the Yavapai and or Mazatsa orogenies. However, there's a paper out there from Rasmussen et al. Where they got similar ages, more like a 1.7 billion years, and they associate that with the collapse of the Pinocchian orogeny. That's just for your information. Then, at about 1.1 billion years ago, there's a clear thermal overprint by an event based on this cluster that's about 1.1 billion years, and it's potentially associated with the Midcontinent Rift System development. And it needs a little further investigation, because if you look at these shards, they kind of align with some of the uranium lead ages, but we have a few dates here that might be unknown thermal events around this time. And actually, there is another project that I will be talking about associated with the Giants Range batholith. And sure enough, these ages come back there too. And that's rather curious. And for the sake of information and to be frank here, this actually was published in Geology in the fall 2025. I'm happy to send you a copy if you're interested. It wasn't published for the longest time because we actually omitted these 2 ages because they were anomalously low, and there wasn't a very good reason for it. And once it was put back, we also received some other results that generated the same dates, which is very, very interesting. So yes, if you would like to read more about this paper, then I'm happy to share it with you, or find Allerton et al. 2025. So we didn't stop, and this is one of the chapter of my thesis. The second chapter, the following chapter, is geochemistry. That's what we are dealing with right now, where we use lithogeochemistry of all the samples and trying to look at element mobility using isochrone analysis, which is mass balance calculations, to look at what's moving in the system, what's steady in the system, and how they compare to each other, and what that means. But the real smoking gun is iron stable isotope geochemistry, because although the dates that we got for the 2 different hematite phases weren't as clear in terms of the perogenesis or their timing relative to each other, iron stable isotope geochemistry, where we look at these 2 different samples and compare it to banded iron formation, clearly show a trajectory from oxides from banded iron formation, less altered to more altered oxides to microcrystalline hematite to microplated hematite. So you can read it in my dissertation, and then manuscript hopefully will be ready sometime the end of this year with also new data that supports fairly new and updated hydrothermal system for the area. Then we are hoping to do more geo and thermal chronology. And why that is because we have hopefully soon a new lab available with different precision of equipment where we can try to lower the error. And how we will do it is first we had to make sure that there is uranium in the system, and we used a fairly large laser beam size to make sure to cover everything. But this new equipment, we might be able to have smaller sizes and be a little bit more on target, and perhaps even double or triple the data points that we do. So maybe we are able to separate these two phases into two different ages and less of an overlapping error. Well, I also didn't mention, and maybe you noticed, is the closure temperature of hematite, because you had that beautiful diagram with all those chronometers, but hematite wasn't there. Why that is because so far, the little dating that has happened with hematite or iron oxides, each system had a different closure temperature. And we actually do this with slow helium experiments. And what would be very nice, and what the plan is to do it for the different phases of hematite, because potentially they might have a different closure temperature. And remember that closure temperature is just telling us about this thermal overprint. And what is important about the thermal overprint that I forgot to mention is that if you remember the map, Sudan is about 40 kilometers in map view from the Duluth complex, which is part of the Midcontinent Rift, the closest contact. So the thermal overprint is very important because that's far away. So we would like to know where that is and why that is, basically. So we have some samples from other ore bodies, the Ely ore body, that those mines are now flooded, but we have some archived samples that we would like to date and see if they were affected by the same event. Therefore, the ore mineralization was at the same time. Then I mentioned this other project, the Giants Range batholith. The Giants Range batholith is in contact with the Midcontinent Rift. Actually, it's igneous suite that's called the Duluth complex, known for the sulfide mineralization. And what we are looking at is a geothermal chronology campaign, and we systematically sampled away from this contact on the surface. And what we are seeing is a systematic difference in different chronometers. We're not only looking at uranium, lead, we do look at it in apatite, in zircon. We also looking at some other systems so that we can put together a nice thermal history. And I also work with Josh Feinberg and undergrad student Celia Cortopassi regarding iron oxides within the Giants Range batholith and trying to match up their story with the geochronology. So these are all very interesting research topics. And another one is also part of my dissertation, and if you're interested in reading about it, we are proposing a geology trail project to show the geology in the Sudan State Park, and also try to maybe in the future put together some educational content for K-12 educators and also for the general public to show what we have here in our backyard. And with that, thank you so much. I'm happy to take any questions. And if you are interested in contacting me and or hear more about the research, please don't hesitate to email me. Thank you.
Thank you, Suzanne. Beautiful lecture. Wonderful, wonderful topics. A lot of information. You could condense several billion years into 30 minutes. It's a pretty good trick there. So you and I were talking a little bit briefly beforehand, and let's make sure that people understand. We have not actually run out of the high-grade iron ore up in that area. There's still high-grade iron ore, but it's cheaper to mine the lower grade than it is the higher grade. Is that correct?
That's correct. Yeah, and that was the economic problem. It was not profitable anymore. And then what they figured out and what happened in the U.S. is they utilized the low grade banded iron formation, the magnetite from that banded iron formation, to turn it into those taconite pellets, and that's much better. And we have a lot more of that than high grade ore. If that makes sense.
We got a couple of questions. Mark Nupin is asking, there's great worry that any mining in northern Minnesota Lakes region will be polluted by any mine. Is there possible that the mine in the lakes region does not pollute all of the lakes? What do you know about that? I know that your pollution is not necessarily your strong suit, but what do you know about mining and pollution up there?
So my area is in Sudan, and that's an inactive mine. And when I look into waste regarding mining in the Sudan, there's not much information about it. I know that, for example, in Hibbing, there's very strict regulations as to even when they planned the mining over there, the whole procedure and the whole regulations, they necessitated to have those like clearly outlined before mining even started. But to be real honest with you, I cannot speak for pollution and mining, because what I'm looking at is inactive areas. However, if this actually expands into Mesabi Range, and if we really can date those ores, then I will need to get more current with active mines and mining regulations and waste, because that's just as important as my research. So
there was another question that had come up about when you're going to publish, and I see that you mentioned that already. Sometime by the end of the year is kind of what you're looking at. Is that correct?
Yes. So the geochronology that I talked about and a bit more detailed characterization, that's already published, and that was published in the fall. And I'm busy with writing up the geochronology, and I also have a conference to attend and show the iron isotope data. And once that's done, and then the last of the data is acquired that we're still waiting for, a few data points, then it's complete. And yes, that should be, I mean, published by the end of the year is very hopeful, definitely submitted. And it depends on how many times it comes back to me, or if it actually gets rejected. So fingers crossed here.
All right, good. Another question, are you able to elaborate on the cause of the 500 million year old thermal events? What exactly triggered those? Can you explain that at all?
The which thermal event?
The 500 million year old thermal events that you were talking about, 500 million.
Yeah. So what we are looking at with I can't give you an event right now. What we are trying to look at with these projects is the extent of hydrothermal alteration. For example, if we associate iron ore mineralization in the Sudan with the Yavapai or Mazatlan orogenies, we are talking about great distances, and we don't actually know that the docking of these origins, how deep their effects go into the crust, and we don't know what happens on the very at the depths, even at the mental level at this point in time. So when we go into these younger events that like the 500 million years, I mean, we actually got with some uranium, thorium, helium ages in Giants Range Batholith, we got everything from like 300 million to 500 million. We are looking into some hydrothermal events associated with regional metamorphism, metamorphic fluids. There's some that's been recorded in Minnesota River Valley area. Again, we are going very far, so the extent would be large. So I don't have an answer to what event could be, but right now what I'm looking at is existing events. But what we think that we might have is events that we haven't documented yet or um, um, haven't realized yet because analyses weren't as high resolution before, if that makes sense.
Okay. Another question came in. Is all this concurrent with the amethyst formations in Ontario? Oh, do you have any sort of chemical relationship to the amethyst formation up near, what is it?
Oh,
Thunder
the
Bay?
Thunder Bay? Yeah, yeah,
Yeah.
yeah. I've been there. I actually dug my own amethyst out, which was like the coolest thing, and hoping to do that later this May. But yeah, that's a very good question. I actually don't know the age of. I know that the host rock is very different. It's sedimentary, and then we have these veins that are quartz veins, and then also, oh yeah, I see a very good question down there. Suddenly it popped up. So I know that those quartz veins have these amethysts mine, but I don't actually remember their ages. However, when we talk about extent, if we figure out what fluids are in there and there are any kind of minerals that can be dated, then we can correlate them, yes. And it's not impossible because in Ontario, Canada, actually, there are a few research papers that are discussing some events associated with burial of the area that actually have dates of 1.7 billion years. So that being said, it might be that our association with orogenic events is maybe off, and maybe we need to look north instead of southeast.
Okay.
So, yeah.
Dave, do you have the chat box open? Are you looking at the chat box?
Yes, I do have. Yeah, I have the chat box open, and a question has come in there from Michael. Could other lenses of banded iron formation affected by shear zones in the Vermilion district match these dates, such as Section 30 mine? Is there a possibility for an age gradient in iron ranges across Minnesota, or a connection with the helium generation in northeastern Minnesota? By any chance, can you read that question?
Yeah, I think so yes. So the other thing is that, for example, in Ely, the BIF is slightly different. So the ore is different. However, if we are staying within the Vermilion district, I believe that the ages should be very similar in the Ely ore, and that's what we're trying to mine. I have the samples, we just need to date them. So that would be, I'm not sure, Section 30. I mean, these samples are from Sibley, and if I said that right, and Zenith Mine, and I'm not sure where in relationship Section 30 is to these mines, but yes, there is a possibility for what you're asking. So yeah, that's very interesting. And then you asked about the connection with the helium generation in northeastern Minnesota. So a fun fact: I went to Perth to do this uranium, thorium, helium analysis, and we have to start with, well, picking the shards, but they are actually packed up into niobium tubes, and then we have to degas them. And for the love of God, we could not degas them. There was so much helium in them. That was the first thing. And then, of course, later on, it percolates out that there's helium found in northern Minnesota, which is associated with the Duluth complex, right? And then these are these pockets, these anomalies that were found. And then there are all these samples that have a ton of helium in them. I don't know the answer, but we thought about it. And yeah, at this point, it's a question. It's a question on my never-ending list of questions. And thank you for asking that. Yeah.
It's good to have lots of questions, right?
Oh, absolutely, absolutely.
Okay, I'm going to read a comment from the chat again from Patrick.
Thank you.
As a history nerd, I love the mix of human history and Earth history. And then, so that's just a comment. And then he says the research paper is and I don't know if everybody
Thank
can read
you.
the chat, but he's got a big link in there, and I can send that out. Otherwise, people can probably copy and paste that into their own on their own computer.
Yeah, I
Chat
think
window.
it's open source, so you should find it. And I see that this one is ResearchGate, so you should be able to. But if you can't get hold of the paper, I'm happy to send it to you. So Steve and Dave and Randy have my email address. So I'm very happy to share that. And I also see that Carolyn wrote that section 30 mine was in Winton, east of Ely. So I wonder if I could, okay. That I could it was very difficult to get samples from those mines, and some of them are not georeferenced, so I have to, in terms of publication, if we date them, it's a little bit challenging when you cannot have the exact location, but you can there's some fantastic miners wrote some absolutely fantastic logs that I can actually trace the samples back. Yeah, I would, if anyone can get me ore samples, this is what the plan is to try to redo these analyses so we can have a better understanding of what affected all the ore. And if you look at so if you think about southeast direction of these orogenies, then that's going to be hitting the Mesabi Range too. So is there a thermal overprint that is similar, and we can maybe date that with the uranium, thorium, helium system on hematite? That would be fantastic. And somebody successfully downloaded the paper from that, so that works. Thank you so much for sharing it, Patrick.
Okay, and then I'm going to go back to the Q&A. Anonymous says, this is not a question, but Sims and Mori published a monograph on the Tower Sudan titled Geologic Sketch of the Tower Sudan State Park in 1966. The
Ooh.
document was available from the Minnesota Geological Survey. So if anybody's interested in that, they should be able to find that from the survey. And if you Google around, you might be able to find it that way. I don't know. Otherwise, if you contact the survey, they should be able to get it to you.
Yeah. Oh, that's very nice.
And then Mary Helen Inskeep. Many of us toured the Sudan mine underground areas and the now defunct physics lab a few years ago. I'm one of the people that did that, by the way. Those are great tours. When you extracted the helium from the samples, did the date of extraction of each sample affect the amounts of helium you were able to extract? That is, if the sample had been dug out 100 years ago, does it yield less helium than one dug out 50 years ago, and even less than a fresh sample?
So the helium should be in a closed system unless the sample is heated up. But the samples that were extracted are from 2016, so fairly recent. I mean, now that's also 10 years ago, and they were put aside in a bucket. There are newer samples now that we're going to date new samples that were extracted from the wall now. So unless nothing happened to the samples, and this is when we're talking about heat, it shouldn't be a problem. Yeah, you often wonder when you crush up samples, and then you know how the grinding can, if something you're using the wrong material, and the grinding can affect the actual accessory minerals that you pull out. So these are all considerations, and unfortunately, when you have samples, that this is why I also really like to collect the sample myself, so I know what happened to them from the get-go. But then again, you're looking at a mine that had also its own life, and tours, and all that. So it is possible that an old sample has a different result. So that's actually very good to so old versus fresh sample. And yes, the samples that I have long time ago, I don't know what they've been through, and that's the risk that you're taking with this. And that's why there's these archived samples from the Ely mines that I'd like to try and see where it takes us. If there's any trace of or anything that we can find that matches what we have, that would be fabulous. So, but yeah, very good question.
Okay. This is the last chance to get any questions in, folks, because we're at the end here. There's one more comment, and I will second that comment. Thank you so much. Wonderful presentation.
Now, Zsuzsanna, you worked with George Hudak, is that correct?
That's correct. I think that's gonna be forever.
Yeah, well, that's good. He's going to be speaking to us in April, so pay attention to our Geological Society schedule, and you'll want to listen in to him, because for as much as you know, and you do an awful lot, this guy has forgotten more in 10 minutes than all of us combined have learned on this stuff together.
Yes.
He's been outstanding.
Yes.
So thank you very much, Zsuzsanna.
And thank you so
I'm going
much.
to interject one more thing here. Early on, you mentioned Mark Jersa's map, and he spoke to us last week. So
yes, that's correct. He is also responsible for my interest, or it's his fault, because the Minnesota Geological Survey has, especially with Terry Borbohm in the beginning, and Mark when I started, they got me very interested in Minnesota rocks, and so he's also a pivotal person in my geologic career. So.
Well, great. Well, thank you very much.
There's a kind of a question from Carolyn. Thanks. Will we see you at ILSG?
Yes, that's correct.
Okay.
I'm
considering going there myself. I haven't made a firm decision on that.
It's gonna be great. It's in Thunder Bay, so we can go amethyst digging.
Sounds good to me. Thank you very much, Zsuzsanna. Thank you all
so
for joining us tonight, and we will sign off for tonight, and we'll see you again in 2 weeks.
Sounds good. Thank you so much for the invitation.
All right. Good night, all.
You too. Thank you.